Right, so last bit for this week is looking at increasing and decreasing functions. So basically we're going to use our differentiation to find where on a function the gradient is positive or where it's negative or where it's zero. So a function is increasing when the gradient f of x is greater than or equal to 0 over a continuous interval. So if the gradient is greater than or equal to 0 over an interval with no asymptotes in it and is continuous, then it's an increasing function. A function is decreasing when f dash of x is less than or equal to 0. So this topic kind of mixes together our differentiation from earlier this week with our inequalities from a couple months ago. So let's go for an example. E.g., let's have just any old quadratic, and we'll have minimum there at -1. So for this graph, if that's our minimum, then it is decreasing for x is less than -1 or equal to -1. So all of this bit here is decreasing. And all the stuff on the right hand side, so all the stuff when it's moving up, it's all positive gradient there, that is going to be increasing. So greater than or equal to -1, positive gradient, less than or equal to -1, negative gradient. So we can try and find the range of a function when the gradient is increasing or decreasing based on whether it's greater than or equal to 0 or less than or equal to 0. So find the region for which this function is increasing. So because it's increasing, we're trying to find when is f of x or f dash of x greater than or equal to 0. So we're going to differentiate this function and then solve the inequality for when it's greater than or equal to 0. So step 1 is to find f dash of x, which is going to be 3x squared minus 5. And that is going to be greater than or equal to 0 because that's what we're trying to find when it's increasing. So to solve this, we can basically say, well, we've got a x squared graph and we want to find when it's greater than or equal to 0. So this graph is going to look something like this. And if we solve where its roots are, we can add the 5 over divided by 3, so we can get x squared equals 5 over 3. So x is plus or minus root 5 over 3. So one of these solutions here is going to be root 5 over 3. The other solution is going to be minus root 5 over 3. So this graph is increasing when this is positive. So our function here is increasing when the gradient function, which we plotted here, is positive. So an gradient function is positive for all values here and all values here. So there are actually two ranges of x values that make our original function increasing. So it's increasing when x is greater than or equal to root 5 over 3, or when x is less than or equal to, what are we doing there? Less than or equal to minus root 5 over 3. So those values make this thing increasing. So this is a cubic. Cubic looks like, you can see that So here's x cubed minus 5x. So we just used this function, we differentiated it, found the range of values for which it's increasing, and if we plot these on the graph, we got minus root 5 over 3 and root 5 over 3. We can see, yeah, it's increasing for less than this one and more than this one, and it's decreasing in the middle, which is what we showed on our quadratic. So this is f of x, this is the gradient, and this is the original. So original and then gradient. So the gradient function, positive here, when the original is increasing. So although it's quite easy just solving the equation, plotting it and using the inequality, remember the thing you're sketching with the inequality is the gradient function. It's a sketch of the gradient. And you can see that this is a quadratic, the original function is a cubic. Here's the original function, cubic. Here's our gradient function, quadratic. So just bear that in mind. Make sure you're clear that the gradient function is a separate thing to the original function. Cool, right, we'll try a couple more of these. So we're going to say find the interval for which so we're going to try and find the interval for which this function is decreasing. So again, first step, find the derivative or the differential function. So x differentiates to 1. 25 over x, we're going to have to rewrite that. So 25 over x, that's basically 25x to the minus 1. So if we want to differentiate that, we're going to get minus 25x to the power of minus 2. So there's my differential function. It's decreasing when this is less than or equal to 0. So 1 minus 25x to minus 2 less than or equal to 0. Now to solve this one this time, we've got a weird looking reciprocal graph. So to solve this, I'm going to rewrite this using my indices again. So 1 minus 25 over x squared is less than or equal to 0. Then I'm going to rearrange this to try and find x. So if I, what should we do? If we add this onto this side, 1 is less than or equal to 25 over x squared, times up by x squared. X squared is less than or equal to 25. And now we can try and plot this. So this is an x squared graph. Move down 25. Solve it to get x equals plus or minus 25. Sorry, it doesn't. This is plus or minus 5. So this, we're looking for when this graph is less than or equal to 0, which is going to be all of this bit. So our original function is decreasing when x is between minus 5 and plus 5. So decreasing when x is less than or equal to 5, greater than or equal to minus 5. So remember, gradient function, we haven't sketched the original function, we just sketched the gradient function and found the values for which it was decreasing. Cool, right, that's it for today. So a couple questions on this. Then next week we're going to look at these very specific points when the gradient is 0, so here and here, and these are what we call turning points, which are minimums and maximums of graphs. But yeah, that's for next week. Cool, cheers guys.